Okay. So what we're going to do now, and for the first month of this class, more or less, is this main course on GR. But we're going to start from the fundamentals. And I'm going to recast, I'm going to present to you essentially Newtonian physics first. But I'm going to do it in a geometric language. And this is all taken from Thorne and Blandford. This is the way they do it, which is why I thought it was a nice way to introduce GR and build up to the numerical relativity stuff. Because I'm going to show you stuff that you're familiar with, Newtonian physics, right? Electrodynamics, you know this stuff. But I'm going to use the language of geometry, which will then be useful when we come to talking about general relativity, right? So recasting all of this in the form of differential geometry. That would have been an epic fail. Okay. So. Again, you know, it's good to write the notes, give you some muscle memory of it, but I will post my notes after this. So the thing about physical laws, draw some vector here in some coordinate system, in some space. Everything that we deal with initially will be in flat space, and it will be called Euclidean space, right? We're familiar with this. It's the Euclidean 3 space that we're all used to doing in our usual physics courses and things like this. So a vector is some arrow in a 3-dimensional Euclidean space, right? It's got some direction and some magnitude, right? Now, if I were to ask any one of you, give me the definition of a vector, what would you give me? What would you say the definition of a vector is?
It's a quantity with a magnitude and a direction.
Yeah, that. Another way of saying it, or let me coax this out of you. If I asked you what's the definition of a tensor, what would you say?
Special case of a matrix. It obeys certain rotation laws.
Which is what you get from Jackson, right? For instance. That's not, that is a limited case of what a tensor is. That is a special case of a tensor. That's not actually what a tensor is. A tensor is a linear function of vectors. Any linear function of some number of vectors. And yes, in Euclidean 3 space, it can be defined and described by its transformation properties. Just like a vector has certain transformation properties that it must obey, so must a tensor in Euclidean 3 space. But that's a special case. So a tensor is a more general geometric object, which is a linear function of some number of vectors. And the number of vectors that it's a function of is the rank of the tensor. So that I coaxed it out of Mike. That's what I was looking for, is the standard, grad level textbook definition of what vectors and tensors are. They obey certain transformation properties, but they're actually more general geometric objects than that. And so we can make a geometric principle for physics. Now you're all lucky. I handwrite in cursive, but when I write on a board, I do block text. So pick your poison. So all physical laws are or can be expressed as geometric relations between geometric objects. I put this as a geometric principle. This is sort of the Euclidean flat space-time variant of the principle of relativity. This is the principle of relativity, but only restricted to a Newtonian framework. Okay? And so what do I mean by geometric objects? I mean scalars, vectors, and tensors. which are all kind of the same thing, right? A scalar is a rank 0 tensor. A vector is a rank 1 tensor. They're all tensors of different rank. They are all this class of geometric object. And so the physical laws can be expressed as simply geometric relations between these different types of geometric objects. The other thing that the geometric principle states, which is akin to the principle of relativity, is that I do not need to specify a coordinate system. I can write down all of the laws of physics, and I can utilize those laws of physics without specifying coordinates, either Cartesian or spherical, or what's the distance between different things, what's the basis vectors that I'm using in my free space. Don't have to define them. These things are completely independent of a coordinate system or a set of basis vectors. And all of these laws, these geometric relations between geometric objects, are the same regardless of what choice you make for basis vectors. There's the principle of relativity, right? Stated in another way. Okay. So let's do some concrete examples here. Let's say that I've defined some origin point to some coordinate system, whatever it is. Out here, I've got some point, some location in this coordinate system. I'll label Q. Over here, there's another point. I'll label P. These are just points in some coordinate system, haven't specified what. I can measure the displacement vectors from the origin of those 2 points, right? And I can also define the vector that connects those 2 points and the distance between them. Some delta x with an arrow on top. As I'm writing on the board and as I write in my notes, vectors will be denoted by the little half arrow on top. That's how I denote vectors. Just FYI. In the book, those will be bold-faced if you're reading the book. I can't do bold-faced on the board. Tried, it looks kind of horrendous. Now, I can define this distance between point P and Q without defining a set of basis vectors and without defining a set of coordinates, coordinate system. And it is, so if I wanted that distance, delta x squared absolute value is just going to be delta x, that guy squared, which I'm going to define here as being some separation between those 2 points, delta sigma. And along that path, I can define derivatives or paths in this space, which don't depend on the coordinate system. Okay, so I can, not only can I define distances, right? Concrete example of this. If I've got some vector in Euclidean 3 space, which is what this pen kind of represents, right? There's a tail, there's a head, it's got a distance, I can point in different directions, right? Just like my vector here. If I asked you, Steve, how long is this pen? How long is this vector? What would you do? Measure it, right? You get a ruler out, you put the ruler down on top of the vector, and you go, it's this long. Did you have to define a Cartesian or spherical coordinate system to do that? No. You just measure it, right? And that's the example, right? That's the point, is that I didn't have to define a coordinate system or a set of basis vectors within which to measure this thing. It just has that. It's an intrinsic feature of this vector, independent of the coordinate basis. You get out your ruler, you measure it. That's how big it is. That's the geometric principle, right? That applies to any geometric object, not just that green vector there. The other thing that I can define without a coordinate system is a curve in this space. And so what I can do is I can start at some point and I can take some vector, which perhaps tells me some coordinate displacement, right? If I treat that vector as some relative speed, let's say, right, of some particle which is moving in this space, and I measure the velocity of that particle at some instantaneous moment, and I said, okay, over some infinitesimally small amount of time, what's the new coordinate? I actually don't need a coordinate system to do that, because the coordinate system is almost self-defined. It's the path of the particle in this 3 space, right? And so it would go here, and then I do the same thing over some infinitesimally small amount of time. I'd measure the velocity, and then I would know the particle is here. I'd measure this velocity. Again, I'm just laying down the ruler on the vector at that location. I'm asking how big is it, and then I'm saying, let's take a really small time step and go a little bit further. And so by doing this operation, you can actually chart out a curve in some arbitrary 3 space without defining a coordinate system. And you do that. What's my little dx here? Well, what it is the change in the location of the point, p, whatever, over some distance, lambda, times d lambda. What's lambda? We call this lambda the affine parameter. It's essentially the particle's own little private coordinate system that it's carrying along with it. It's its curve through some arbitrary 3 space independent of a coordinate system or basis vectors. We call that the affine parameter. And this dx is a differential distance, meaning infinitesimally small, right? As I take the limit, right? Standard way that you would do a derivative, right? Working from the Leibniz principle on up. Differential distance, okay? And so I can do this, and I can chart the trajectory of some particle in this way without coordinates. Okay. More than that, if I can do that, and necessarily to do what I'm describing to you, I have to be able to measure that particle's velocity. And I can do that pretty easily. So if that particle is moving through some arbitrary 3 space and some unit time dt, then its velocity vector is just the change in its differential distance at some point divided by some unit time of infinitesimal time, right? And you're going, at this point, this guy's just pulling the wool over my eyes and he's just writing down basic calculus. Yes, I am. But what have I not done is define my coordinate system, right? All of these things are independent of those coordinate systems. You know that, right? If you were to write down some hairy integral, you wouldn't decide on your coordinate system until you went to actually maybe integrate, right? You'd write down integral of something dv, where dv represents the volume element, the infinitesimal volume element. It's only when you go, okay, I'm in E and M and I've got some point charge. Okay, r squared sine theta d theta d. Okay, let's do this. It's only when you actually went to compute it that you would need to define your coordinate system. And that doesn't change the physical relationship, right? That doesn't change the physical law. And if we were to do this, if we were to take this velocity at all the little new points p that this particle found itself moving on, if we were to define and calculate this vector at each one of those little points, we would end up with, let me just call this what it is. This is a vector, right? Obviously. We would end up with v of p, the location of the particle, right? We could do that at every single one of those locations, right? I haven't defined x, y, and z. I haven't defined r, theta, phi. I've just said along the path of this particle, here's its velocity. This is now a vector field. Partially, this is an opportunity for me to do some glossary terms, right? A vector field. Okay. Another thing that we can define, another geometric object that has to do with the behavior of this particle is the following. We would say if the vector v at some point p, which is now a function of lambda, the affine parameter, right? So I come here and I say, which one of these p's am I talking about now? The only coordinate is the affine parameter. If that is not equal to the velocity at some if this velocity is not equal to this velocity, right? Move along the affine parameter, recompute the velocity. Those two things aren't equal. right? The velocity is not constant, then I have an acceleration, right? Something is changing the velocity. And I can then define the acceleration, which is simply that change infinitesimally over dt. Again, trivial calculus, right? An important point to make here, though, is that this object is also a vector. It has some direction, right? It has some direction. And so doing that operation of measuring the infinitesimal change, taking the derivative, essentially, in time, doesn't change the rank of the geometric object. It's still a vector, right? There are other geometric operations that we're going to do that can change the rank, right? You need to be aware of that. Okay. Okay. Another thing that this is going to obey is that if we take this and multiply by a scalar, we still get a vector, right? So take any vector, multiply by a scalar, you still get a vector. For instance, if I were to take that guy, take the acceleration a, multiply by, I don't know, call it m, maybe the mass of the particle. Still a vector, and we're going to give that vector a definition. Why don't we call it the force? Right? Still a vector, even though we've multiplied by some scalar. The scalar doesn't necessarily need to be a constant in all of free space. It doesn't have to be. In this case, maybe we're assuming it is, right? Because the particle mass isn't changing. But it doesn't have to be. It doesn't have to. All right. So that's a long-winded way of arguing that we can pretty much describe most all of physics without specifying a coordinate system. And we still have it yet, right? All of these things that I have drawn, talked about so far, are free of some basis vectors. And does that make sense? I won't belabor that point anymore. Okay, now let's talk about tensor algebra, which is what we've been doing, you just didn't know. It's what you've done all your life in physics, whether you knew it or not. Because a scalar and a vector, tensors. Okay. So, we've already said this. In flat space, a vector is defined by some length plus a direction, right? We said that. That's what it is. It's got some direction, it's got some length. We don't need basis vectors to understand that. The other thing about a vector is if we were to, where's my vector? We were to take this vector here, and we were to do some translation to it to some new point in some arbitrary Euclidean 3 space. Is it a different vector? No, same vector, right? And what I did here is an operation that we would call parallel transport. So if I move a vector in some arbitrary Euclidean 3 space in a way that does not change that vector's direction or its length, that's called parallel transport. That's one way of defining parallel transport, but also vectors are defined by the parallel transport. A vector is something that doesn't change under parallel transport, right? That's the transformation law way of defining what a vector is. Okay? Important. But they're somewhat more general objects than that. Okay. Now, a rank in tensor, underline that guy, because those are important. Tensor is, I said this already, a real valued linear function of n vectors. The book has kind of a fun way of thinking about this. A real valued linear function of n vectors. So the way that the book makes this diagrammatically, it's kind of fun, is Kip and Roger had this idea that a tensor is like a box with slots. Some number of slots on the top. The number of slots on the top is the rank of the tensor. And into these slots, I can put vectors. And if I put vectors in each one of the slots, out the side, like some ticker tape, comes some number. In this case, it happens to be 42. A real number, right? Pictorially, when I first read that, I was like, what are they smoking? And with Kip, it was something. This is being recorded. Kip's great. But now, you know, it actually has incredible power to define it in this very abstract way. You got to put in the vectors before you get out some value from the tensor. And if you put in vectors into each one of the slots, what have I done? What happened to my tensor? I reduced it all the way to a scalar. And so by filling all the slots in a tensor, I reduce its rank to 0. And thus it is just a real number. And so that's what happens when you fill all the slots of a tensor with vectors. You spit out a scalar, a real valued number. Okay? When I write tensors on the board and in my notes, there's many different ways to write tensors. So apologies. This is a tensor T. I give it horns. Hook them. 1, because I like the horns. 2, this is the way that I was taught. Okay? So it's like my vector arrow, but now I mean this. Now, it sort of doesn't matter because a vector is a tensor. But at least when I do it this way, you know I mean something that has rank in excess of 1. All right? I might also do something like this. If I'm writing in completely coordinate-free notation, I will do something like this to indicate the rank of that tensor. Those are the slots. So this is that. 4 slots on top, 4 slots in the parentheses. That tensor is a function of 4 vectors. Linear function of 4 vectors. Okay. Okay. So now, I've said all of this in words. And again, you know, if you're not writing down everything I say, I'm not writing on the board everything I say or everything I've written in my notes. You can just go and grab the notes. I'll post them. Okay. So linearity. What do I mean by linearity? A linear function of vectors. Linearity implies the following, that if I've got some tensor and into it I have input some vectors into its slots, we're going to say that this is a rank-free tensor, okay? And now I don't have empty slots. So now I've taken vectors and I put them into the tensor's slots, and I'd like to get out of this some real number. But in this first slot, I have the sum of a scalar times a vector. What's the rank of that? What's the rank of that object? Scalar times a vector. 1. It's a vector, right? Plus another scalar times a vector. Thus, what's the rank of this whole thing? 1. It's a vector, right? Vectors plus vectors are vectors. No problem. Okay, but I've got this thing in there. It's not just a simply expressed single vector, right? It's this more complex object, and then just regular vectors in the other slots there. Linearity of the tensors implies the following, that this is equal to this. linear function. That's all I need. Make sense? That's easy. It's no problem. Okay? Okay. The next tensor algebra object that we're going to need and rely on somewhat heavily is the inner product, or often referred to as the dot product. In coordinate-free tensor algebra, the dot product is defined as the metric tensor. Now, the metric is something that we're going to encounter a lot of. But the simplest way to define that metric tensor is it's the tensor that gives you the inner product. It defines what the inner product is in some space, right? Euclidean flat space, even in curved spaces, okay? So I'm going to represent that by G, and it's a tensor, so it's got horns. A, B, all right? So this is, in particular, the metric is a rank 2 tensor. It is a linear function of 2 vectors. If I stick vectors A and B in there, by definition, this is A dot B. By definition. That is how we define a metric. Now, another fun thing about the metric is that if you look at this, since A dot B is equal to B dot A, the metric tensor is symmetric. Or we might say, more precisely, it is symmetric in its 2 slots. I can interchange A and B in this and get the same number out. Right? The other thing to note about this is if I fill both the slots in the metric tensor, I reduce to a scalar. What's another way of saying dot product? Scalar product, right? We sometimes call it scalar product. We take 2 vectors and we make a scalar. But what we're actually doing is filling the slots in some rank 2 tensor and outputting a number. Okay. All right. Another useful thing. We've got the inner product. Now let's talk outer product. Sometimes referred to as the tensor product. Where the inner product reduced the rank of our geometric objects, the tensor product is going to increase the rank. Okay. Where am I? Okay. So in other words, I can take some vectors. This is the symbol that we use to represent the outer product or the tensor product. A, B, cross. It's not really a cross product. Anyone got a favorite way to pronounce this operator? I'm going to probably resort to just calling it cross, but that's not right. Circle cross. Okay. That gives us a tensor. In particular, it gives us a rank 3 tensor. Okay. Notice that this gives us a tensor with open slots, right? I've increased the rank, not decreased the rank. This is not a scalar, right? This is not equal to the tensor of A, B, and C, right? That's not the same thing. That's not what we've done here, okay? We've constructed a higher rank geometric object, taken 3 vectors and made a rank 3 tensor. So the way that I would get a scalar out of this is I could literally write notation something like this, where I've got my tensor products, have built me up some tensor object, and then into this object, I can insert into its slots 3 vectors, right? And this will give me then a scalar, right? And so this thing is defined to be A operating on E times B operating on F times C operating on G. So I've taken this object, I've put the vector E into vector A's one slot, and so on and so forth. So this is a demonstration, a representation, a proof, I don't know if it's a proof, that vectors are tensors. Vectors are rank 1 tensors. A vector is a linear function of one other vector, and that gives a real value, scalar, right? So each one of these is essentially a scalar product, right? So this is a scalar, that's a scalar, that's a scalar. 3 scalars times each other is a scalar, so this is a scalar, right? So I've taken the rank 3 tensor that I constructed and reduced it back down to a real value, a number, okay? Now I printed out my notes, and it literally cut the page right in the middle of one of my handwritten lines. So this is going to be a fun section now. Questions so far? This is all very dry, but we're going to set the framework for a lot more sophisticated stuff. To work the problems, you're going to need to have these tools at hand. Okay? So, since vectors are rank 1 tensors, we can say the following, that if I take vector t with, tensor t, tensor product into tensor s, and then into that I insert, this is where it's going to get fun because this is cut off. I can go to this page. Yeah, that's what I thought. Vector E, vector F, and oh, here we go. I think I didn't do anything fancy here. Yeah, that's right. H, J. Okay, so I've taken this 2 tensors, I've tensor product them together to create a higher rank tensor, and that then is defined to be tensor T operating on E and F times tensor S operating on G, H, and J, just like that. And that gives me a scalar, right? Here I've assumed that this is rank 2 and this is rank 3. So if you tensor product a rank 2 and a rank 3 tensor, you get a rank 5 tensor. And here I've stuck 5 vectors into the 5 slots of that resulting tensor. And this is just sort of notation, right? If I were to write it out this way, this is how you would arrange the various vectors into the different slots. Okay. Tensor contraction. I hope I get to this today, but there's, in my opinion, there's an easier way to write all those notation, but you kind of got to go through this stuff before you get to the, the promised land. Okay. So a contraction is defined as follows. We can say any tensor can be defined as a sum of tensor products. So I can take any tensor and I can re-express it as some sum of tensor products. In other words, my tensor T, I can write A tensor product B plus C tensor product D plus so on and so on. What rank is T? 2. Okay. And we can construct, therefore, we can construct the inner product from the outer product using this inner product from the outer product. What do I mean by that? Okay. Okay, so contraction lowers the rank by 2. Okay. Contraction lowers rank by 2. So if I take a rank 2 tensor and I contract both its slots, I get a scalar. Easy peasy. Okay. But an example of this, I'm going to write the following way. 1-3 contraction, by which I mean contracting on slots 1 and slots 3 of some tensor. And in this, I'm going to put A, tensor product B, tensor product C. There's my rank 3 tensor, plus E, tensor product F, tensor product G, plus on and on and on. If I contract on slots 1 and 3 of this rank 3 tensor, I define that as being A dot C times B plus E dot G times F, and so on and so forth. These are outer products, and using contraction, I've ended up with inner products. What's the rank of this object? 1. It's a vector. All right. So I've contracted on 2 of the slots of the tensor. Slot 1 and slot 3. So I've reduced its rank by 2, and a rank 3 tensor goes to a vector on contraction. Okay? So this is the vector. All right. That's most of the machinery that we're going to use. Inner products, outer products, these different relationships and behaviors of the tensors. I think I have time to get through this one last thing, which is just an example, a very brief example. And then next time, we'll rewrite everything in index notation, which makes life a little bit easier. But the thing about index notation is that it often is presumed that if you put indexes on something, you have defined components of a vector or a tensor. If you've defined components, you've defined a set of basis vectors in which those components are measured. So all of this so far has been in completely coordinate-free language, no basis vectors, right? Completely coordinate-free. We will talk about defining a coordinate system and using index notation in a coordinate system. But let's talk very briefly, last thing today, I think, particle kinetics in this geometric notation. So we've already kind of talked about, we've got particle trajectory. I'm going to say that's x of t, where t is some coordinate time. It's some universal time. Okay? So t is universal time. Now, this reminds us that we're in Newtonian flat space, Euclidean 3 space, right? Because I have universal time. I'm treating it as this some weird thing. You know, everybody's got the same clock. It ticks at the same rate. Time and space are not intertwined, which they are, and we'll get to that. But let's pretend, for now, that time is universal. So I can write down some trajectory of some particle, its position as a function of time, similar to what we did before when we didn't have coordinates and we defined things along an affine parameter. I can compute that particle's velocity as a function of time by taking the differential changes. Its momentum is just p. These are all vectors still. And then its acceleration. Of course, we're just going to say that's a of t. Okay. So by definition, we know that v of t is simply the differential change in its position over some infinitesimal interval of universal time. That's all that is. And the momentum, P of t, is just the mass of the particle times its velocity. Nothing relativistic about this yet. Remember, we're just doing Newtonian for now. And the acceleration as a function of t, dv dt, which is now the second derivative of the position. Again, you're going, well, duh, right? And the particle energy we're going to define as 1/2 mv squared. I mean, I guess I could put a hat on that. Some interesting things going on here, right? The energy is a scalar. So I've taken a dot product there, right? Taken an inner product and reduced my rank 1 vector. So I've taken that vector v and I put v into its one slot. And then I've reduced it to a scalar, which gives me the energy appropriately weighted. Okay. Points in Euclidean 3 space, locations, right, are geometric objects. I don't need to define a coordinate system to know that there are points in space. So all of these things, which depend only on the trajectory, right? I've written down everything so that it is essentially some geometric relation of the trajectory of the particle. All of these are also geometric objects, which means they are independent of the basis vectors we choose. In other words, they all transform like vectors or tensors, as it were. Okay. From Newton's second law, we know that the change in a particle's momentum as a function of time is equal to the force acting on that particle. Right? F equals ma, dp dt. Now, we haven't defined what forces might be acting on that particle, but let's say that there is the Lorentz force. All right? So this particle is interacting with some electric and magnetic field in space. In which case, now I have a definition for my force law. It's the charge of the particle times the electric field plus V cross B. Do not confuse this E with this E. I'm sorry I used the same E. Maybe it would be less confusing. Of course, the energy cannot be a vector, right? Let me specify this as capital E maybe. Okay. So now I've defined my force law. Okay. With all of these, I got time. This is quick. So all of these are geometric. I don't have any coordinates yet. I can actually do some physics without defining coordinate systems on coordinate-free geometric objects. So I can show, let's show, and this is in your book, exercise 1.1, show that, show the energy change of this particle interacting with some field E and B is the following. So dE, I did it again, sorry, don't write that. D capital E dt is Q V dot E, where that's the electric field, okay? Show that the change in energy of some particle moving and interacting with an electric and magnetic field is that, okay? So we've already defined our energy to be 1/2 mv squared, okay? So now differentiating that guy, I'm writing fast, I'm gonna make more mistakes and end up going slower. dt, we're just gonna take the derivative of this thing, equal to 1/2 m times the derivative in time of v squared, which is equal to mv dot dv dt. Okay? Just chain rule there. Now, this guy has got to be equal to ma, right? Clearly. That's just the mass times the acceleration, which has got to be equal to my force law, which again, I've already defined here to be Q E plus V cross B. Cool. Therefore, if I just work this out now, d dt is V dot Q times electric field plus V cross B, which is Q. I'm just now doing some chain rule. Q V dot V cross B. Okay, I'm just chain ruling in there with my inner product. That's all I'm doing. Okay, I can re-express this bottom equation right here using just a identity, a vector calculus. Okay, I can rearrange the inner and cross products so that I get something along the lines of this. That stays the same. And what I can do is I can rearrange that product. I'm at will to do this. What's a cross product of a vector with itself? 0. That term goes away. Thus, we are left with that which is to be proven. I didn't define any coordinates. Okay, that's true. That was a trivial problem, right? But I didn't have to talk about components, right? There was no components of the vectors. There was no x, y, z. There was no r, theta, phi. There was just using geometric relationships between the geometric objects to do some physics. All right. I almost got through all of my notes for today. That's not bad. Questions? All right, read chapter 1 for Thursday, please. Take a look at the homework, but don't expect you to really start on it. But please read the book. You'll rehash a lot of the stuff that I just did here on the board. And then we will finish the rest of chapter 1 on Thursday, one way or another. Because next week, we'll move on to special relativity, which is chapter 2 in Thorne and Blanford. All right, thanks.